So I ran into a situation the other day where a servo didn't behave the way I expected, and the thing I read on the internet was actually wrong. At least it was kind of right, but it was wrong at the same time. And I think it's because somebody didn't realize that the timers they were using were different and they got it to work. And so let's just talk about it a little bit. So basically servos operate on a pulse width modulated basis. And so they have a period of 20 milliseconds. And in that 20 milliseconds, you can have a rising pulse in that window continually as those windows flow by of 1 to 2 milliseconds. And because in a lot of these applications, we want to stay in integer math, we actually convert that into microseconds, and that becomes 1,000 microseconds to 2,000 microseconds. So from 0 to 180 degrees on a servo is from 1,000 microseconds to 2,000 microseconds. Now, it turns out servos have a little more range than that. That is actually the official standard, but typically people widen that a little bit to try and get 180 degrees out of it. So again, we're using integer math for everything, so we're going to do it in microseconds, even though the pulse specifications are essentially in milliseconds, but it's all the same because it's just time. So we go from 600 microseconds to 2,300 microseconds. So that's the industry standard servo is 1,000 microseconds to 2,000 microseconds, and we actually tend to drive them from 600 microseconds to 2,300 microseconds. But so how do we get there, right? So we need to generate that pulse. We have start with degrees, 0 to 180, or we could do radians for those really smart people, not me. And the end result is we need a certain size pulse out of it, and this all gets wound up in the timers. So the way these hardware pulse modulation works is there's a timer. I'll go into this. I got a picture here. But the thing that drove me to this was actually like, I had moved from an ESP8266 to a Pico, Raspberry Pi Pico, and that thing, the servos work great on an ESP32 and an ESP8266, and then I ran it on a Pico and it just did not work. And then I found this thing that said, hey, you actually need to set your numbers from 1,000 to 9,000. And I'm looking at that, and I'm like, you know what? It turns out that you do set the numbers from 1,000 to 9,000, and that's because we're using a 16-bit timer instead of a 10-bit timer in some of the others. But they are not microseconds and they are not degrees. These is actually clock ticks. As it turns out, it is not time and it is not angle. It is the count of clock ticks. So this is really pretty much wrong. But they were to get the right answer for the wrong reasons, right? So you're broken if you get it right, if it works. So let me just look at this again. So if you look here, like in the position 0 for a servo, the window, the period for a servo is 20 milliseconds. And so inside that window, we can provide any pulse we want, but really the ones that work is 1 millisecond to 2 milliseconds, or that 600 to 2,300 microseconds, right? So it's 1,000 microseconds to 2,000 microseconds. The rest of the pulse is idle. You can try doing the rest of this. You'll just fry it. Don't do it. So we're going to translate this into 600 microseconds to 200 microseconds. Again, all the APIs are trying to use integer math, so we wouldn't put this in milliseconds, because it'd be like 0.3 milliseconds, and that would be horrible. So they basically just scaled this up, right? And so like I said before, the standard allotted times, you'll see this. You can set your servo from 600 to 2,300. What that really means is you're going to set the pulse size from 600 microsecond pulse to a 2,300 microsecond pulse. That's pulses. That's these guys, right? So the question is, how does the hardware map? So we map degrees into that range. The range is 180 degrees. So that 600 to 2,300 is 180 degree spin, right? And so then somehow that microsecond pulse needs to be loaded in the pulse width modulation hardware or software. And so it really comes down to the timer, how the timers are implemented, because that's actually what we use for these. If we want them to be super reliable, we'd like hardware timers even, right? So basically the pulse width modulation is driven by the hardware timer. And the timers are programmed for two things. One is, what is their entire period, right? What is the window? So in the one I showed above, this would be 200 milliseconds. This whole window would be 200 milliseconds, right? So we need to program the timer's counter to run at a rate where the counter goes from its maximum number to 0 in that time window. So if I was on a 10-bit timer, I have 1,024 steps. So I need to cover those 1,024 steps in 20 milliseconds. That is the period. And what it's going to do is it's going to repeat whatever it does every time it runs through a period, right? And so the second part of what we need is what part of this the pulse is actually going to be up, right? So the full length of this is the full counter. And then we're going to, and so if it's like 1,024 ticks, right? That's 100% of the time this thing, and we just set the clock rate. So we need to run 1,000 ticks in 20 milliseconds, right? That's actually the math that goes into it. That thing will start clicking away and it'll repeat. Now we need to set the pulse width. So we need to tell it how many ticks out of that 1,024 is going to be up and the rest of it's going to be down. So in this case, if I was going to be 10%, right, and I had a 10-bit timer at 1,024, if I needed 10%, so 10% of 200 milliseconds is 2 milliseconds. On my servo, that's 180 degrees, right? We went from 0 is 1 millisecond to 180 degrees in 2 milliseconds, right? If I have a 20 millisecond timer run, the period's 20 milliseconds, then 10% of that would be 2 milliseconds, and that would be, I need to somehow make this work for 2 milliseconds. So you can kind of think of it as having two counters, right? One is the outer counter that is the hardware timer. It just counts down, blip, 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 blip. And then we decide how long the pulse is. We tell it how long the pulse is in ticks. So if I had 1,024, I would tell it 124 ticks, right? And so if I program the timer to run in a 20 millisecond period, and then I tell it I want the uptime of the pulse to be 102 ticks of that, then I will end up with a pulse that looks like this, right? Set the total time in the timer. Why do we care about this? Why? Because there's libraries that do this, so what do we care, right? Here's the explanation of this with a 100-step timer to make the math easier. And I'm going to show you why this matters, and it matters because if you use the library or you did, like, you know, if you're on Arduino, they have like an 8-bit timer, and if you're on an ESP32, it's a 12-bit timer by default. So, you know, and I'm using MicroPython, so I don't even know what's happening under the hood. So if you look at it, so if we know, we set the total time to run for the time to count down all the way to the bottom, from top to bottom in the period, 20 milliseconds in this case, because we're running 50 hertz on servos. If you were doing LED PWM, the numbers would be different, right? But the timer calculation for the LED is going to be identical to this, just with a higher hertz. You might be doing 500 hertz, right? But the rest of this, how the pulse width modulation, how many ticks are applied in the up to light up, that with the 500 hertz would actually make it flash quicker, so that some people wouldn't see the persistence problem, right? And then you would decide how many ticks it would be up to set the brightness in that 500 hertz, right? Which would be 2 milliseconds, right? So basically, the number of ticks that we're going to want that to be up is going to be the pulse width in seconds times the number of timer steps times the frequency in hertz, right? And the same equation is going to be the number of ticks I want this to be up is the pulse width in seconds, which is always going to be the pulse width in seconds is going to be 1 to 2 milliseconds, right, or 1,000 microseconds to 2,000 microseconds. The scale of the number of steps is the size of the timer, and the frequency is going to be 50 hertz for servos, 500 hertz for LEDs, and you invert that to get the period, and that's so we can make the math easier, right? So a servo pulse of 1 to 2 milliseconds is going to be about 5 to 10% of the 20 millisecond period. So it'll be about 5 to 10% of the ticks will be for when it's powered up, right? So if we convert that to millisecond math, why did I do that? Because we're going to do microsecond math, because you see it anyway, right? So basically, if we multiply, if we had it before, we had it in seconds, and I would like to do milliseconds. So basically, I'm going to just multiply everybody by 1,000, and that tells me what my math looks like for milliseconds, right? So it turns out the number of ticks is before I had the pulse width in seconds times the scale times 50, right? Because that's the hertz. Now I'm just going to divide everybody by 1,000. So the pulse width in milliseconds times scale times 50 divided by 1,000, because we still have this 1,000 on the bottom, or you can just divide the whole thing by 20. You'll see that. The reason I'm not putting this in here is because you'll see it in people's code. Actually, I have it in my code this way. The one that's important is microsecond math. The APIs run in microseconds because we're doing integer math for everything. So all the math has to be optimized for integers with less rounding errors, right? So in our case, we had this thing where we did this milliseconds one before. So let's look at what the microseconds would look like. The number of ticks is the pulse width in seconds times a million times the scale times the frequency divided by a million, right? That's because we multiplied the top and the bottom by a million, okay? And the reason we did that is that makes this be in microseconds, okay? Because we're going to, the scale needs to be the same. And so if we have this other number by a million, that effectively makes all our numbers in microseconds. So the pulse width in microseconds times the scale times 50 divided by a million tells us how many ticks we need, right? So if I have this counter running along, and whether it's 10-bit, 15-bit, 100-bit, it doesn't matter. The timer's going to take, at 50 hertz, it's going to roll over every 50th of a second, right? And we need to know how many picks before it rolls over is going to be high. So in this case, it is the number, how many microseconds we want. That would be 600 to 2300 times the scale divided by 20,000, right? Or times 50 divided by this. You can do it either way. So if we look at it, right, the ESP8266 has got a 10, oh man, this turned long, got a 10-bit timer, 1,000 steps. The Pico has a 60-ish timer. It's really 255 times 255. So its roller is 65205. So what that means is whenever I need to set the PWM value, the tick count that actually gets set in the library for the Pico is going to be like 62 times whatever it would have been on an ESP8266, right? One has a 0 to 1024 range. The other's got a 0 to 5,000 range. So if you look at it, I'm just going to show you. Basically, if we need 1,000 microseconds and on a 24-bit timer, and we divide by 20,000 because we multiply by 50, divide by whatever it was, 1,000. We end up with 51 ticks, and that's not a lot of resolution, right? So we could, if any drift, we're going to see that. So if I need a 1 microsecond, 1,000 microsecond, meaning at 0 position on the servo, it's going to be 51 clock ticks. The pulse will be high. And if we want it to be at 180 degrees, it'll be 100 clock ticks, right? So, and if you do it in milliseconds and microseconds, the math comes out the same. The key point here is you got to know how many bits your timer is to know what those numbers should work out like. On the 16-bit, it's a little different, right? So if you need 1,000 microseconds, it turns out we need 3276. And that kind of makes sense. It's 5% of the total counter, right? So 2,000 micromums. That should be microseconds, right? If I need that would be 10% of the duty cycle of 20 milliseconds, then it would be 1/10 of the total clock would end up. And so then you just have a range in between for all the other angles. So that's it, right? Basically, most libraries set the length at 600 to 2,300 microseconds. And then under the hood, you do this math. You got to know which timer you use. And you actually find in MicroPython, they have one for 10-bit timers, and they have underbar 16T, which is actually the 16-bit timer. And the default, I think, is like the 10-bitter or the 8 on the Avtel. Anyway, that's it. I hope that's, I ran long. So that's it. If you really get hung up, you got to understand, we're actually programming in time. That time gets converted into ticks based on the size of the timer. Have a great day.